Hi everyone. In this video, we will discuss about the short-term deflections of uncracked members. Short-term deflection refers to the immediate deformation that occurs in a prestressed reinforced concrete member as soon as the load is applied. It means that bending or deflections which occurs immediately after applying the load are known as immediate deflections. We may also call it as a instantaneous deflection, mainly due to elastic deformation. Elastic deformation means the structure returns to its original shape. It returns to its original shape when the load is removed. Returns to original shape when load is removed. It means that if you remove the load, it regains its original shape. Then we can call it as a elastic deformation, right? Short-term deflections are also known as instantaneous deflections or immediate deformations. Generally, these short-term deflections occurs due to self-weight of the beam, live loads like traffic loads, floor loads, etc., and the prestressing force itself, which may cause upward or downward deflection depending on the tendon profile. That's why these short-term deflections generally depends on the modulus of elasticity of the concrete. If modulus of elasticity is increases, deformation will be decreases. Next, moment of inertia of uncracked section. It means that moment of inertia means we can call it as a shape, right? Short-term deflection will also depends on the shape of the structure. If we have large moment of inertia, it means it is more stiffer. Deflection will be less. Next, bending moment. If we apply more movement, it deforms more. Next, flexural rigidity, EI. Flexural rigidity. From these parameters, we can call generally why I am telling this short-term deflection depends on E, I, M and flexural rigidity. How can we remember? See, we know this formula, right? M by I is equal to F by Y is equal to E by R. Generally, deflection may have some radius of curvature. That's why I am taking these values. M by I is equal to E by R. From here, 1 by R is equal to M by EI. That's why I am telling. This is some deflection we can say. Now coming to E. Deflection inversely proportional to 1 by E. That's why E increases, deflection decreases. Next, moment of inertia. I increases, deflection decreases. Similarly, flexural rigidity. Flexural rigidity itself increases, deflection decreases. Deflection is directly proportional to movement. Movement increases, deflection also increases. Right? that's why I am telling short term deflections generally depends on E, I, movement, flexural rigidity. In addition to this, deflection, short term deflection also depends on the eccentricity. Eccentricity. If eccentricity is more, upward prestressed deflection will be more. Prestressed deflection will be more. Right? Next, span. As usual, if span increases, deflection increases. Span increases, deflection increases. Profile type. Generally, straight tendon profile cause no deflection. Deflection is 0. If you are maintaining a parabolic profile or a harped profile, then the deflection will be upward. Means you may observe some camber. That's why profile of tendon will also affect the direction and magnitude of the deflection. Okay, direction and magnitude of the deflection. Next, type of loading. See, generally point load induces more deflection than UDL. Point load induces more deflection than UDL at a same intensity of loading. Okay, short term deflections are generally depends on modulus of velocity, moment of inertia of uncracked section, and movement, flexural rigidity, eccentricity, span, profile type, and type of loading. Right? Now, generally we use Morse theorems to calculate slope and deflections of prestressed sections as well. From Morse first theorem, the change in slope between 2 points is equal to area of M by I diagram between those 2 points per unit width, we may call, or unit span. Right? The change in slope between 2 points is equal to area of M by I diagram between those points. Similarly, if you want to determine the deflection at a point relative to the tangent drawn at another point, right? Deflection is equal to movement of the area of M by I diagram about that point. Right? I am repeating it again. Deflection at a point is equal to M by area of movement of area of M by I diagram per unit span, we may call. Generally, there are mainly two types of short-term deflections we observe in prestressed structures. One is due to precessing force. It is a primary deflection. The precessing force, when tensioned, applies an upward camber. upward camber. When we tensioned a tendon, we may observe some upward camber in a beam. This camber is beneficial to counteract downward deflection due to loads. To counteract downward deflection due to loads. I am repeating it again. When we are tensioning a tendon, it induces, suppose this is the beam, this is the tendon. When you apply a tension here, this beam will induce some camber like this. This camber is also beneficial to counteract deflections due to loads. The magnitude of camber is generally depends on the eccentricity and profile of tendon. Okay, this magnitude of this camber is depends on the eccentricity and profile of the tendon. Now, coming to the deflections due to external loads, these are secondary deflections. Secondary deflections. Generally, these deflections caused due to loads, either self-weight or dead load, caused due to loads. These deflections are always downward. These deflections are downwards. And opposed to prestress induced in the camber. Right? As I told you earlier, once this camber has been formed due to prestress, the load imposes some downward deflection against to the camber. This is a downward deflection, right? Now next, to solve the problems, we will see some standard formulas for uncracked simply supported beam. If the simply supported beam subjected to UDL load, then the deflection due to UDL load is 5 WL power of 4 by 384 EI. Here W is the UDL load, L is the span, E is the modulus of velocity, I is the moment of inertia. If it is a point load, suppose this is the simply supported beam, the load is at a midpoint, then the deflection is equal to PL cubed by 48 EI. Next, in the above case, it is the simply supported beam is subjected to UDL of W kilonewton per meter length. Okay, then your deflection will be 5 WL power of 4 by 384 EI. Now coming to prestressing force. This prestressing force induces positive camber, means positive deflection. Formula for the deflection caused due to prestressing force with an eccentricity E is PL square E by 8 EI. PL square E by 8 EI. Okay, 8 EI. Now see, this is a primary deflection, this is a secondary deflection. These two are secondary deflections. This is a primary deflection. Now if you want to determine the total short term deflection, you need to sum up these two deflections, primary and secondary deflections. Then you can get total short term deflection. We will try to solve a problem. See, the deck slab of prestressed concrete culvert is made up of a slab of thickness 500 mm, and this slab is also spanning over 10.4 meters, and it supports a total UDL of 23.5 kN per meter square, including dead load as well. And modulus of velocity of concrete is given as 38 kN per mm square, and this slab is prestressed with straight cables. It's very important. Straight cables. Prestressed with straight cables. Here we can see it is straight cables. We may write with this one. It is straight cables. Straight cables are prestressed with 1200 Newton per mm square, and the cables used are 12 high tension wires of 7 mm dia, and all these cables are at an eccentricity of 195 mm. Right? We need to determine the instantaneous deflection. We will draw the figure first. Suppose this is the deck slab. The thickness of this slab is 500 mm. Span. The span is around 10.4 meters. And it is having the load of 23.5 kilonewton per mm square. 20 kN per meter square. Next, modulus of velocity is 38 kN per mm square, and they used 12 wires of 7 mm dia at an eccentricity of 195. Means this is CGC. The cables are placed straight. The cables are placed here with an eccentricity of, what is this here? Eccentricity is equal to 195 mm. Now we need to determine the instantaneous deflection. Right. Total instantaneous deflection is equal to deflection due to prestressed force plus deflection due to load. In the case of simply supported beam, deflection due to prestressed force is already we discussed, P times L square multiplied by E divided by 8 EI. Now deflection due to self-weight and dead load, that is deflection due to load, is 5 times W times L power of 4 by 384 EI. Right? In the question it is clearly given that 7 mm dia wires, total 12 wires. 12 wires of 7 mm dia were pre-stressed with 1200 Newton per mm square. It means that a cable is formed by 12 wires of 7 mm dia. Now the force in each cable is force is equal to total 12 wires of each dia 7 mm, right, times 1200, that is equal to 5 7 square 7 square divided by 12 into shift to pi 7 square into 1200 divided by 4, that is equal to 554.176 newtons. If you convert it into the kilonewtons, now 554.176 kilonewtons, right? 554.176 kilonewtons. Now see, the space between one cable to another cable is given as 328 mm. It is given in the question. The space between each cable is the space between two cables is given as 328 mm square. Now I would like to know how many cables are there in width of 1000. In width of 1000, how many cables are there? To determine that one, number of cables in 1 meter span, that is equal to 1000 mm divided by 328, that is equal to 1000 divided by 328, that is 3.048. This number of cables are there in 1 meter span. Now total force is equal to 3.048 times 554.176, that is equal to 3.04 times 554.176, that is equal to 1689.5 kilonewtons. This is total force P, total prestressing force P. Now we know P, we know the length, we know the eccentricity, we know modulus of velocity. We need to determine I value. I is equal to BD cubed by 12. Here B is 1 meter, that is 1000. D is equal to 500 cube 12. The answer is that 1041 multiplied by 10 cube mm power of 4. Now if you substitute this value, deflection due to prestressed force is equal to P times 1689.5 multiplied by L. What is the span? Span is 10.4 meters multiplied by 1000. Now I am converting in meters into mm square multiplied by E. What is eccentricity? 195 divided by 8 times modulus of velocity is given as 38 and I value 1041 times 10 cube. Now the value is at 11.28 mm. 11.28 mm. Now we need to determine deflection due to load, that is 5 times WL power of 4 by 384 EI. Now here we need to determine the weight. Weight is given as, what is the load given? 5 times W, 33.5 km per meter. Now I am converting it into mm. 0.0335 kilonewton per mm multiplied by, what is the span? 10.4 meters, converting it to mm, power of 4 multiplied by 384 times 38 times 1041 10 cube. The answer is that 12.90 mm. See, precessing force will act upward direction. This deflection will be in downward direction. That's why total force is equal to 11.25 plus 12.9. See, generally if it is a upward direction we can take negative sign, if it downward direction we can take positive, then the value will be 1.65 mm. That is, positive means downward direction, downward, right? This is the answer. Suppose there will be a additional question, that is, what is live load? What is the magnitude of live load? What is the magnitude of live load? Which nullify the deflection due to prestressed force and load. We got this value as, now we got this value as 1.65, right? We got this value as 1.65. To nullify this value, how much of live load we need to place on the structure? To determine that one, already we know the deflection due to any load is given as 5 W L power of 4 by 384 times flexural rigidity. What they are asking, if this value is 1.65, how much of weight we need to place? This one we need to determine. That's why if you need the weight, 1.65 times 384 times flexural rigidity. What is the E value? E value is 38 into 1041 times 10 cube divided by 5 times span is given as 10.4 into 1000 square. Right? The answer is that 9.26. we need this much of UDL. We need this much of UDL to nullify the deflection of 1.65. Okay. This is the amount of live load we need to nullify the deflection of 1.65 caused by both prestressed force and load. Thank you.